Homework 4.1 Exponential Functions, Video 5. Homework due May 29th at 11:59 p.m. Before we go on to the next topic, I neglected to mention in the previous video the homework problems that are associated with that and this video. In the previous video it said 1 through 5, but that was left over from before. It should have said 6 through 7. So the previous video and this one are associated with questions 6 through 7 on the homework. In the previous video, we discovered what the graph of an exponential function looked like if its base was greater than 1. So now let's see what it looks like when it's less than 1. Now keep in mind that by definition of exponential functions, the bases will never be 0 or negative. So when I say less than 1, I really mean less than 1, but still positive. So for example, we're going to graph f of x equals 1/2 to the x power. Now these things are left over from the previous graph, so if you're taking notes, don't write them down yet, but I wanted to leave them up there to see which of these stay the same and which ones change, and you might be surprised. Okay, so let's work them out. 1/2 to the x, starting with 1/2 to the third. Well, if we multiply 1/2 times 1/2 times 1/2, oh wait a minute, we don't have to do that. We have an exponent rule that says you can distribute a power across a fraction. So we can just distribute the 3 across and give it to the 1 and to the 2. 1 to the third power is 1, but 2 to the third power is 8. So 1/2 to the third power is 1/8. What's 1/2 to the second power? Using the same logic, on the top 1 squared is 1, but on the bottom 2 squared is 4. So 1/2 to the second power is 1/4. And 1/2 to the first power is easy because anything to the first power is equal to itself. But what about 1/2 to the 0 power? If you're still thinking 0, you need to purge that from your subconscious. Anything to the 0 power is 1 as long as the base is in 0. This is something to the 0 power, it's equal to 1. So now things get interesting. 1/2 to the -1 power. I think maybe we should work this one out. There's a couple of ways to approach this. The first is to distribute the distribute the power to both halves of the fraction. But let's actually do what a negative exponent says to do. A negative exponent says to do the reciprocal of the positive exponent. So 1/2 to the -1 power equals 1 over 1/2 to the positive 1 power. Well, I know what 1/2 to the positive 1 power is, it's 1/2. But how do we deal with this? How do we deal with 1 divided by 1/2? I'm sorry, did I say divided? I meant to say over. 1 over 1/2. Actually, that's a lie. I meant to say divided. Because if you view this complex fraction as a division problem, not 1 over 1/2, but 1 divided by 1/2, hopefully your brain goes, I remember how to divide fractions. The rule for dividing fractions is to keep the first number, change it to multiplication, and reciprocate the second number. So 1 divided by 1/2 is the same as 1 times 2 over 1, but that's just 2. That was a whole lot of work just to say 2. Oh, but wait a second. When we did this in the previous video, didn't we say that a number raised to a negative power is the reciprocal of the number raised to the positive power? So 1/2 to the -1 power should be the reciprocal of 1/2 to the positive 1 power. We did. It's just that in this case, the things that we're reciprocating are already fractions, and so when we reciprocate them, they become, in this case, whole numbers. So if that's true, and it is, then this should be easy to finish. 1/2 to the -2 power is the reciprocal of 1/2 to the positive 2 power. So it's the reciprocal of 1/4. It's 4 over 1, also known as 4. And 1/2 to the -3 power is the reciprocal of 1/2 to the positive 3 power. So it's the reciprocal of 1 over 8, which is 8 over 1, or just 8. It's almost like we're getting the same answers, but in the reverse order. It's not almost like it is, we are. I wonder why that is. There's a reason why. In fact, let me go ahead and tell you the reason why, because I'll forget by the end of the video. There's a reason why we're getting the same answers here, but in the reverse order as when it was 2 to the x power. So I'm going to do a little bit of what I call smoke and mirrors. I'm going to take this function and I'm going to manipulate it. I'm going to massage it a little bit, make it look different. How am I going to do that? Well, first I'm going to go inside where the 1/2 is and write it as 2 to the negative 1 power. Think about it. That's a legitimate move. 2 to the negative 1 is the reciprocal of 2 to the positive 1. And don't we have an exponent rule that says when you raise a power to a power, you multiply? We do. So I can multiply the exponents. Negative 1 times x is negative x. So there's two ways to view this function, as 1/2 to the x power or as 2 to the negative x power. So we're still finding powers of 2, but before we do, we're sticking a negative on the exponent. This is 2 to the negative 3, 2 to the negative 2, 2 to the negative 1, 2 to the 0, 2 to the first, 2 to the second, 2 to the third. So it's not a coincidence that these outputs are the same as before, because 1/2 is 2 to the negative 1 power. But I digress. Let's sketch this graph. Before I sketch it, I want you to see if you can either visualize what it's going to look like or manually sketch it on your own. You've got all the information you need, and I'll give you a hint. A lot of these things are still going to be true. This time the low end is on the right. Over 3 up 1/8 is barely off the axis. Over 2 up 1/4 is a little bit higher. Over 1 up 1/2 is halfway up. But then over 0 up 1, look, we have the same y-intercept. That makes sense. Anything to the 0 power is 1. But now, negative 1 is up 2, negative 2 is up 4, and negative 3 is up 8. So we're getting the exact same picture, except in reverse. In fact, you could say that this graph is the mirror image of the previous graph across the y-axis. So which of these characteristics are preserved and which ones have changed? Is the y-intercept still 1? Are there still no x-intercepts? Yes. Is there a horizontal asymptote on the left of y equals 0? Well, not on the left, but it's still y equals 0, so there is still a horizontal asymptote here, but it's on the right. Is it still increasing? No, it's not. From left to right, it's decreasing. So that changed. Is the domain still negative infinity to infinity? Yes. Is the range still 0 to infinity? 0 to infinity. Yes. So the only thing that changed is things relative to being left and right. Horizontal asymptotes on the right instead of the left, and it's decreasing instead of increasing as we move from left to right. This type of graph is called exponential decay. Exponential decay. They are a real-life phenomenon that are modeled by exponential decay. In other words, their values drop off real fast and then the growth rate slows down as time proceeds. One common example is the value of a car. You buy a brand new car and drive it off the lot, what happens? The value depreciates right away. Although it doesn't start at infinity, the price of your car, the value of a car will decrease like this. Now that doesn't mean the value will eventually be 0. The horizontal asymptote might be higher. Like I just sold a junker for $450 a few months ago. It was good for parts. It started, it just needed a new transmission. But anything that decays like this is called exponential decay. Another common example is carbon dating. For example, when a geologist discovers a dinosaur bone, there's a test to estimate how old it is. The test is based on two assumptions. Number one, based on the size of the bone, when the dinosaur was alive, it had a certain amount of carbon in it to begin with. And number two, carbon decays like this. They know the decay rate of carbon, so by measuring the amount of carbon that's actually in the bone, and compared to how much it should have been based on the size of the bone, they can calculate how long it's been decaying, and therefore estimate the age of the bone. Half-life of radioactive elements decay exponentially. The value of things, and what's the other one I said? Oh, carbon. Carbon is really just another half-life issue, but those are a couple of examples of things that decay exponentially. So, if an exponential functions graph, if an exponential function's base is less than 1, then its graph models what's known as exponential decay. If it's greater than 1, then its graph models exponential growth. In the next two videos, which should be the last two, we'll talk about taking these graphs and moving them around and maybe flipping them as well. Oh, wait. Hopefully you didn't stop the video. I wanted to follow up on something. Earlier in the video, I did some hand waving and said, look, this is the same as 2 to the negative x, which kind of makes sense based on the negative exponent rule. But what was the original graph of 2 to the x without the negative? This one. So in other words, without the negative, it would be the green graph, and with the negative, it would be the red graph. So what effect do you think the negative had? What do you think the negative did to the green graph to turn it into the red graph? Reflected across the x-axis. In the next videos, we'll talk about different changes to functions that cause things like reflections or translations, which is just sliding the graph around.